The centroid is the geometric center of an object, often labeled with this symbol. The centroid is useful in solid mechanics as it is the point about which an object will bend, twist, or deform depending on the force applied to it. For a rectangle, finding the centroid is easy because it is right in the middle, halfway up and halfway across. I'm going to use y bar to represent the y coordinate of the centroid and x bar to represent the x coordinate of the centroid. For composite bodies, such as this one, we can separate it into rectangles and then take the average position of their centroids weighted according to the area of each rectangle. In other words, we can use this equation. Y bar is equal to the sum of y bar dash a dash over the sum of a dash. Y bar represents the centroid of the whole shape, while y bar dash is the centroid of each individual rectangle, and a dash is the area of each of those rectangles. We can also do the same thing for the x component. X bar is equal to the sum of x bar dash a dash over the sum of a dash. The x equation is just the same, except that x bar dash is the horizontal distance to each of the centroids. This can be really confusing, so let's do a quick example. Say we need to find the coordinates x bar and y bar of the centroid of this L shape. We'll start by breaking it into rectangles. Doesn't matter how we break it up, just whatever's easiest for us, so I'm going to break it up here. We'll call this rectangular area A1 and this one A2, and draw in each of their centroids. Now let's write our equation for x, which is still here on the left, but I'll write it again just for clarity. So on top of the equation we have x1 a1 for the first box added to x2 a2 for the second box, and we divide all that by the sum of the two areas. So subbing in the values, we have x1 equals 10, a1 is 20 by 50 millimeters. Oh, I should have probably added into the question that all these things we're dealing with here are millimeters. x2 is equal to 35 and a2 is 30 by 20. Now let's make sure we divide by the same areas, 20 by 50 and 30 by 20. Chucking that into the calculator, you have 19.38 millimeters as the result. Now let's do the same things for the y components, y1 and y2. I'm going to write it down here so we just don't run out of space. Now let's write our y equation again. Y bar is equal to y bar dash a dash, and that's summed over the sum of a dash. Just like with the x equation, we'll expand that so it's y1 a1 plus y2 a2 over a1 plus a2. Now to sub all those in, we have y1 equals 25, a1 is 20 by 50 still, y2 is 40 and a2 is 30 by 20. We divide by 20 by 50 plus 30 by 20 for the areas, and when we put that into the calculator we get a result of 30.63 millimeters. And therefore the centroid is at 19.38, 30.63, and that's millimeters. You see, there's something really nice and simple about these equations. They are linear sums. This means that they work in both addition and subtraction. So instead of just using rectangles which add together to make a shape, we can also subtract rectangular areas to find the centroid as well. Let me show you what I mean by using the same example we just did. This time, instead of using rectangles, let's say that this shape is made out of a big square A1 and a smaller square A2, with the centroids as shown. Now we use the same equation that we did before for x, and this time x1 is 25, a1 is 50 square millimeters, x2 is 35 and a2 is 30 square millimeters. And now when we put it into the calculator, if I'm right, this should give us the same answer as before. And it does, 19.38 millimeters. I hope you found this video helpful, and please leave a comment below on what you'd like me to cover next.